Good evening. My name is Ottmar Edenhofer. I'm the director of the Potsdam Institute of Climate Impact Research and also professor of economics at the Technical University Berlin. I'm very happy and very proud that today we have the opportunity to discuss the outcome and the results of the sixth assessment report of the IPCC, the state of science. And we are very happy that we were able to convince two very distinguished speakers to present these results. And I think these results are important and interesting for natural scientists, but also for economists. And let me introduce our two distinguished speakers. First, I would like to introduce Frederick Otto as a physicist by training, and she obtained her doctorate from the Free University in Berlin in philosophy of science, which is very interesting that she combines the two cultures, so to say. After 10 years at the University Oxford, she joined the Grantham Institute at Imperial College London in October 2021 as a senior lecturer in climate science. Her main research is on the understanding whether and to what extent extreme weather events such as droughts, heat waves, and storms are made more likely or intense due to climate change. Freddie is a lead author of the chapter of extreme weather events of the Intergovernmental Panel on Climate Change. And in this capacity, she will present the results of the report, but also her own research results. In 2021, Freddie was recognized of her co-founding of the World Weather Attribution on the Time 100 list as one of the world's most influential individuals, according to the renowned Time magazine. Our second distinguished guest is Professor Lieberman. He's a colleague of mine at the Potsdam Institute. He is a professor of the dynamics of climate systems. And he is also affiliated as a senior research scientist at Columbia University in New York. And he's also a department head at the Potsdam Institute since 2012. Anders studied physics and he earned his doctorate in theoretical physics at the Weizmann Institute in Israel, and his doctor thesis dealt with fractal fracture and growth processes. As a climate scientist, he is focusing on tipping points of complex natural and societal systems, and he will talk today about the concept of tipping points and explain precisely what this means with this concept. Anders has published more than 130 scientific papers in journals such as Nature, Science, PNAS, and he is a very influential figure in evaluating sea level rise, and he has also a broad range of media contributions, and he is in Germany one of the public intellectuals to explain climate science and also climate policy. So that's great that we have you here, Freddie and Anders. So a few housekeeping issues. So now we will have two 20 minutes presentation, starting with Freddy Otto on extreme weather events and the attribution problem, and then Anders will follow on tipping points and sea level rise. After that we can open the floor for Q&A. And then 6:30, we will close this hopefully interesting seminar. So with that, I would like to hand over to Frederick and ask you, Freddie, to start with your presentation.
Thank you very much. Mar has said I'm working on extreme events and whether and to what extent they are changing because of climate change, and will in this talk mainly focus on how the most recent IPCC report has assessed the latest science on this, but also talk a little bit about how the science beyond IPCC is is progressing, and also particularly where we still have research gaps. But before talking about extreme events, I would like to start with attribution, and with the very first figure of the summary for policymakers of the IPCC report that was published in August, and with the very first statement of that report, which is human influence has warmed the climate. And of course, that is very, very old news. We have known that for a very long time as scientists, and it has also been a statement that in similar versions have been in all IPCC reports that have been published. But what is different this time is that, in contrast to all the other almost all the other statements in the report, this sentence, this statement has no uncertainty language, and that is because there is no uncertainty around this. This is stated as a fact. So in the last IPCC report, it was said that human influence has, it's virtually certain that human influence has warmed the climate, and this is now, there's absolutely no, not even a theoretical possibility that that could not be the case. So this is scientifically very boring, but politically an important change in this IPCC report compared to the last IPCC report and all the IPCC reports before. And so how do we know that? And we know that because of the signs of attribution. And what you can see here in this slide on the left-hand side is figure 1 of that report, which shows in black the observations of global mean temperature averaged over, so global mean temperature, so averaged over the whole globe since 1850 until 2020. And you can see very clearly that the temperature is going up. And it's the more you come to the present day, the steeper the curve is rising. And what you can also see on this slide is in orange, simulations of the climate system response to increased to changes in drivers of global mean temperature, which is changes in solar radiation, changes in greenhouse gases in the atmosphere because of burning of fossil fuels, but also changes in aerosol concentration in the atmosphere. And you can see in green, the climate system response simulated when you only take all known natural drivers of global mean temperature. And you can see that while in terms of the ups and downs and the troughs that you, for example, when you see here this dip in 1991, which is after the eruption of Mount Pinatubo, that is something that you see in both in both simulations and in the observations. But what you don't see in the natural simulations is this very strong increase. So basically what we mean with attribution is we try to explain what we observe with what we know are drivers of the system. And we cannot explain the observed warming without human influence on the climate system. And when you look on the right-hand side of this figure, this is basically showing the same thing, but the contribution of different known drivers of climate change quantified. So you have here the gray bar is the increase in global warming, which is 1.1 degree since the beginning of the Industrial Revolution. And you see that in here in red, we have the total human influence is 1.1 degree. And when you split that up in different components, so this is this larger bar here, which is approximately 1.5 degrees, is just the greenhouse gases from human influence. And then you have this blue bar, which is actually going down, so has about minus 0.5 degree of global mean temperature, that is the other human drivers, and that's mainly aerosols. So if we just had the greenhouse gases and not also the aerosols, global mean temperature would actually be higher than what we observe now. And you can see that there's basically absolutely nothing coming from changes in solar and volcanic eruptions over the long term, and also for internal variability. So in other words, all of the observed warming is attributable to human influence. So this is the global mean temperature, which is what we most of the time talk about when we talk about climate change, particularly in political context, and when we talk about mitigation, so limiting future emissions of greenhouse gases and other and also short-lived climate forces. But of course, that is a very abstract number. No one is experiencing global mean temperature, but what we instead, how these changes in global mean temperature manifest is through changing likelihoods and intensities of extreme weather events. And so we have already 1.1 degree of global warming as assessed by the IPCC report at the point of in the decade when this report was published, which means that the climate has already changed quite a lot. We are long in the era of loss and damage. So climate change is not a future problem. Climate change is absolutely a problem of the present. And also, and I think this is really important and something that I think also the discussions, or at least the closing of the discussions at COP26 showed again, when we talk about climate change and when we talk about climate change in political context, it's still often seen as a future problem only. And 1.5 degree is seen as a sort of a magic number, and until we reach 1.5 degree, everything will be fine. And that is, of course, not the case. The climate system is not a bomb that will suddenly explode at 1.5 degree or at 2 degrees. But every degree of warming changes many aspects of the climate system. And so every degree and every 1/10 of a degree and every increment of warming has influences and leads to losses and damages, particularly for the most vulnerable populations and ecosystems. And so I think this is really important not to forget when talking about climate change, and that the framing that these numbers that we have decided on in a political process are numbers that avoid a lot of the most dramatic impacts of climate change if we keep to 1.5 degree or well below 2 degrees. But it absolutely doesn't mean that the climate isn't changing and that there is not huge amounts of loss and damage we have to deal with and we have to adapt to. So that's so far to the framing. How do we know this? So the main idea behind attributing individual events is actually very straightforward. It is, and it's the same that we have for global mean temperature, only that you need to use different mathematical methods. So you can't do a simple regression because usually the observed records are not long enough, and the signal is not so obvious that these methods work very well. But instead, what you do to find out whether and to what extent man-made climate change has altered the likelihood and intensity of extreme events is you want to compare what is possible weather in the world we live in today with possible weather in the world that might have been without climate change. So in the world that only has the natural drivers in it. And we can do that by using observations and statistical modeling, but also primarily state-of-the-art climate models that are basically the same kind of models that we also use in the weather forecast. And then what attribution studies ultimately do is firstly find out what is actually the event in question. So it might be there's a heat wave, and so we want to know what's the role of climate change in a heat wave over the UK. Then we find out, okay, the first thing is what is actually this heat wave? And it might be that we decide that the best way to characterize this extreme event is by looking at 3-day average temperatures, because that is what really affects heat stress for the human body, which is the main impact of heat waves. And then we need to find out what are possible 3-day average temperatures in the UK in the summer in the world we live in today. And then you can come up with, in this schematic here, with a probability distribution, and everything above a certain threshold causes excess mortality. So you characterize that as your heat wave, and then you have a likelihood of this event to occur in the world we live in today, which might be a 1 in 10-year event. And then we do the same thing for the world without man-made climate change. So simulating possible heat extremes in the world without climate change, you might find that in this case, we have a very different distribution, where the threshold we characterized our event with is only 1 in 100-year event. And because the only difference between these two worlds is man-made climate change, we can attribute the change to climate change. That is the principal idea behind event attribution, which is in theory really not difficult. Doing it in practice is often difficult because it is not always obvious what actually a meaningful characterization of extreme events are, and there is not the one right answer. It very much depends on vulnerabilities. So if vulnerabilities of ecosystems might be very different to people, to economic systems. And then there's also, you require decent observational records to actually find out what's happening in the real world. You require climate models that are able to reliably simulate the type of event you're interested in, which is in some parts of the world and for some types of extremes a challenge. But so there are lots of practical difficulties, but theoretically, the principle behind it is what I've just characterized. And so these studies have been around since, well, the first study of this kind has been published in 2004, but the science really took off since 2012, when there were annual assessments published and more scientific studies on different extreme events. And so this IPCC report that was published in August is the first that has actually systematically assessed our understanding of how climate change has already affected the world in how it has affected extreme events. And so one of the key findings is that climate change is affecting every region across the world, and that human influence is contributing to observed changes in weather and climate extremes everywhere. And this is illustrated with these hexagon figures, which are also in the summary for policymakers as figure 3. And what you see in this figure is in red. So every hexagon is a region of the world. They are chosen by climatic characteristics. And every red region shows a significant observed increase in heat extremes. And the dots on these hexagons show the confidence we have in the attribution to human influence. So where you see 3 dots here, we have high confidence that what we observe can be attributed to human-induced climate change. And you can see for heat extremes, basically everywhere in the world, we see an increase, and generally the attribution to human influence is there. This looks quite different when we look at the next part B of that figure, which is for heavy rainfall. While on a global scale, it is likely that the main driver of observed global scale intensification of heavy precipitation is climate change. We don't have that level of certainty and confidence on the regional scales. So again, in this figure in green, you see where climate change, where we observe an increase in heavy precipitation, and the dots represent the confidence in attribution. And so there are two things to note here. First of all, there are many gray hexagons, and these gray hexagons are regions of the world where we do not have enough literature, scientific literature, that allow us to make an assessment on how heavy precipitation has changed in observations and on whether or not that is due to man-made climate change. And so this, because the IPCC is not doing any new science, but just assessing the literature that's out there, that means that there are quite huge gaps. And these gaps are very much in the global south compared to the global north. There are also this white striped hexagons, and these are regions where we do have enough data and evidence to make an assessment, but there is no clear signal of how the heavy precipitation is changing in that region. And you also see that in many cases, there's just one dot for the attribution, even where we have a strong signal in the observations. And that also often is not that climate change is not that we don't believe that climate change is playing a role, but because of limitations of attribution studies for the types of events in that region. And so the last part of that figure is on agricultural and ecological droughts. So that's droughts that are primarily driven by soil moisture deficits and evaporation. And you can see that there's a lot more evidence, so there's a lot more literature on drought, but that in many cases, droughts are not changing in terms of likelihood and intensity, and that is actually expected. So not all extreme events are getting worse because of climate change, especially in the non-drought prone areas. We don't expect and we don't see a change in the likelihood of drought. But in the already drought prone areas like Southern Africa or the Mediterranean and in Europe, we do see a strong increase that can also be attributed. So that's climate change up till now, the present day. But of course, we already have 1.1 degree, and this is not climate. The climate is not. Climate change is not halting no matter what we do tomorrow. So we will see more and further increase in global mean temperature, and that for many types of extreme events means we will see a strong increase in these extreme events. And here, this figure shows for different future warming levels, how different types of heat extremes are changing. So this is the 1 in 10-year event on the left and the 1 in 50-year event on the right. And when you just look at the intensity change and also and the likelihood change for these events, you can see that the increase is stronger for the more extreme event. And you can see that a heat wave, the same heat wave, the 1 in 10-year event heat wave in a 1.5 degree world would be approximately 2 degrees warmer than in a world without climate change. But it's really important to keep in mind that this is a global aggregate of how heat extremes are changing. depending on where in the world you are and also how extreme the event is to start with, these changes can be orders of magnitude larger. So this is an example of the study my team and I have done earlier this year on the heat wave in Canada and northwestern US. And that event would have been almost impossible to occur without man-made climate change. So climate change made an event that had a likelihood that is almost impossible to characterize. An impossible event is now, in the world we live in today, still a very rare event, still about a 1 in 1,000 year event, but 1 in 1,000 year events happen in a big place like this world quite frequently somewhere. But in a 2-degree world, this type of event would be expected to happen every 5 to 10 years. So for the global averages are not always indicative of or are not indicative of what's happening at the scale of where people actually live. And so this is the same figure, but for heavy rainfall and droughts. And you can see that also for heavy rainfall events in the global aggregate, you see that the intensity of these events is increasing and the likelihood is also changing, but the likelihood changes are smaller compared to heat extremes. So for heat extremes, climate change is an absolute game changer, whereas for heavy rainfall events, climate change often plays a role. And when you look at this map at the top, which shows the increase in heavy rainfall projections for a 2-degree world, you can see that heavy rainfall, and this is important, this is not average rainfall. Average rainfall is not changing, increasing everywhere. Average rainfall is increasing in some regions and decreasing in others. But heavy rainfall is in a warming world increasing almost everywhere. This is not the case for droughts, as I said already. As with the attribution and the observed changes, droughts are increasing primarily in already drought-prone areas. And you can see at the map at the top where these areas are: Southern Africa, the Mediterranean, parts of Australia, South America, and parts of North America. And these numbers at the schematic here are only for these drought-prone areas, the changes in drought. So they are increasing in these areas, but not in other parts of the world. And so this is, this is my last slide. I'll just very briefly like to mention that, of course, I've talked about only 3 types of extreme events now: extreme heat, heavy rainfall, and droughts. They're not the only types of extreme events that happen and that we have evidence for. But these are the ones where we have the most evidence for, and so it's possible to make aggregated figures in the IPCC. There are also changes in tropical cyclones, but there we have only good evidence in the Atlantic basin, but not so much in most other parts of the world. And of course, there are lots of compound events, so hot and dry at the same time, and sea level rise compared with heavy rainfall, which often have the largest impacts. And I would like to finish with this slide, which is just an indication of the gaps in our knowledge. So here you see on this map in red, death from extreme events for the last 15 years. And the larger the circle, the more death from extreme events in that country have been recorded. And it's important to say that they have been recorded, because especially in developed countries, there are also a lot of recording gaps. So we don't know all the impacts from extreme events. So this is an underestimation. And the circles are always on the capital of the country. And overlaid in black circles are those extreme events, or the death associated with those extreme events for which we do have attribution information. And you can see that there is a huge gap in knowledge on many extreme events that have happened in the past in parts of Africa, in parts of Asia, so basically everywhere in the global south, compared to the global north, where you can see here, this is a big heat, this is for Russia, where there are lots of death associated with heat extremes, but where we do have understanding of the role of climate change. So this is really just as we have made huge progress in the last 5 years, because in the last IPCC report, there was no information on the role of man-made climate change on individual extreme events at the scales where decisions are made. But there is still a lot of work to be done to get a more comprehensive understanding. And I'll leave it at that. Thank you.
Thank you very much for this very clear and excellent presentation. Before I hand over to Anders, there's a question in the chat which you might answer immediately. So the question is, as you showed with the current studies, increase in precipitation and droughts have not been linked to climate change in the same way as extreme heat. Could this change in the future, or does it mean that these two extreme events are less affected by climate change?
So it means that the change is stronger for heat and cold, also cold extremes, only that they are decreasing. So for temperature driven extremes compared to rainfall driven extremes. So that's just a physical characteristic. So that will also not change in the future. But that doesn't mean that the small change, the comparably smaller changes in heat in heavy rainfall or drought are not important, because we are only adapted to a very, very stable climate that we have adapted to over hundreds of years. And so even small changes can have huge impacts. So just because heat extremes are changing stronger doesn't mean that the smaller changes are not relevant.
Okay, thank you very much. I would like to encourage all the participants to raise your questions into the Q&A function. But now, thank you very much, Freddie. I would like to hand over to Anders, and Anders will explain us the concept of tipping points in the context of sea level rise. Anders, please.
Yes, thank you very much. Perhaps I can add to the last question. For every degree of warming, there is on average 7% more water vapor in the atmosphere. And it has been shown in a number of places that the extreme rainfall events scale quite nicely with the amount of water vapor in the atmosphere. This is not a statistical statement and it's not an attribution statement, but it means that we also have to expect more extreme rainfall events and flood events in the future, if we further increase the temperature of the planet. So what Friederike just explained is the most important impact of climate change on society. In my opinion, that's not a physical assessment, that's a personal assessment. I will now talk about sea level rise and climatic tipping. Both are much slower, but have a very large scale. So it's worthwhile. They play a major role in the political discussion too, and it's interesting to understand them. They can actually be understood relatively simply in many cases. Sea level is rising simply because the Earth is warming, and therefore also the ocean is warming, and there's thermal expansion of ocean water, similar to air that takes more room and is rising when it's getting warmer. Also water expands if it gets warmer, especially when it's salty. This is was the major contribution to the sea level rise that we have seen over the past 100 or 150 years. The next most important contribution was the melting of mountain glaciers. But increasingly, especially over the last 20 years, the ice sheets on the on the globe, and these are in Greenland and in Antarctica, have increasingly contributed and acceleratingly contributed to global sea level rise. Now, higher sea level isn't a problem, but a rising sea level is a problem because we've built so much of our infrastructure and our cultural heritage and our real estate and our life near the coasts worldwide. Sea level will continue to rise, and this is a figure from the last IPCC report on the sea level rise. You can see here the different scenarios. The 1.9 scenario here, the SSP 1.9 scenario in the warming space will most likely keep you below 1.5 degrees. The scenario of 2.6 will keep you with a certain probability below 2 degrees. And the other scenarios give you higher numbers all the way up to 5 degrees of global warming, plus or minus a little bit at the 8.5 scenario here. These are the sea level curves that give, that you get for the different warming scenarios. And you can see already that there's a significant overlap in these curves. And the reason for that is because there is a certain inertia in the climate system with respect to the warming, in the sense that the CO2, if we increase the CO2 concentration, then we will see this increase in the CO2 only 20 years later. So the warming that we are currently observing has been caused 20 years ago, roughly. This is obviously not a precise time statement, but an average estimate. So the CO2 change that we are currently causing will change the temperature in 20 years from now. The sea level is responding to this warming again with a time delay. And that is why the sea level rise will continue for several hundred years into the future. In the same way as we are now remembering the Greeks as the people who gave us democracy, we will be remembered in hundreds of years, potentially thousands of years, as the generations that have started sea level rise that's still ongoing. So sea level rise is very much about cultural heritage. But you can see here already that there is a curve in this IPCC report, which has never been shown before in previous reports, and that is a very low likelihood event, but very high impact storyline. And this relates to tipping elements. If you actually go further into the future, you can see that the scenarios, this is, if you like, you could call that a Paris Climate Agreement consistent scenario, even though it's on the upper end of the Paris Climate Agreement, will give you up to 3 meters of sea level rise in the year 2300. And this illustrates, as I said earlier, that sea level rise will continue even if we drastically reduce global warming. However, the sea level rise that we will eventually get strongly depends on whether we further increase the CO2 concentration of the planet or not. This you can see at the SSP 8.5 scenario here, which gives you up to 7 meters. And in the low probability but high impact possibility, which is associated with tipping elements, as I'm going to explain in a minute, you can get up to 15 meters of sea level rise by 2300. And just to illustrate this, and for those of you who don't live near the coast and don't know what that means, that would mean 15 meters of sea level rise would be no New York, no Hamburg, no Shanghai, no Calcutta, and no New Orleans, Florida would be gone. So how does this low probability, high impact event can unfold? How can this happen? Well, for this, I would like to introduce you to the concept of tipping points and tipping elements of the climate system. There was an original very influential and very important definition by Tim Landon and John Schellenhuber and colleagues, and Stefan Ramsev of the Potsdam Institute and PNAS in 2008, that defined a tipping element as a system that has a strong response to a relatively small change in the forcing. So a relatively small change in the global mean temperature leads to a very strong response of the system. And you can see an example here. This is the death curve, if you like, of coral reefs on the planet, published by Katja Frieda and colleagues, where you see that even at a warming level of 1.5 degrees, you have practically 100% death of coral reefs on the planet. Now, this definition is very useful from a societal point of view, because as a society, you can define what is a small change in warming. 0.5 degrees is a relatively small change in warming. You can decide as a society, and you can also decide what is a strong response of the system. However, scientifically, this is less easy, because you have to actually say what does strong mean in both cases. So there's an alternative definition that gives you almost the same tipping elements, but is a little bit more precise and also reflects this term tipping a little better. So I just want to give this here because it's an easy way to understand tipping points. So I defined the tipping of a system, or a system being a tipping element, when a system reaches a tipping point when its dynamics gets dominated by a self-amplifying, a positive feedback, until it reaches a qualitatively different state. And let me briefly explain what that means, and then I'll show you what this has to do with sea level rise. An example of that is not a dynamic tipping point, following the second definition here, but would be a tipping point in the original definition, is what we just saw, the death of the coral reefs, because there is no feedback between the global mean temperature change and the coral reefs. So the coral reefs simply respond to a change in climate and very strongly respond to it. But the death of coral reefs does not, the bleaching of coral reefs does not feed back onto the global mean temperature. In most other tipping elements or tipping systems that show a tipping point, this is not the case. There is this kind of self-amplification feedback, and I want to discuss these very briefly here. With, first for West Antarctica and East Antarctica. Antarctica is huge. Antarctica, here you can see Antarctica pushed over North America. It's as big as North America from Mexico to Canada. And it was predicted in 1978, when I was 5 years old, by John Mercer, without the use of computers, without the use of satellite data, that the West Antarctic ice sheet, this is this part here, the smaller part, could become unstable if we continue to increase the temperature of the planet. Now, by unstable, John Mercer was a glaciologist, so he was a physicist. By unstable, he meant a self-amplification feedback. And in 2014, on a Monday in May, 2 papers came out, one by Eric Grignot and colleagues, and another by Ian Jockman, that supported a paper 1 month earlier by Favier that all said the Western Arctic ice sheet has now been destabilized in Amundsen sector. And what happens when this, what does this destabilization mean? You can see here a cut through an ice sheet in Antarctica. And what we are actually interested in when we talk about sea level rise is the flow across what is called the grounding line of the ice sheet. This is the place where the ice becomes afloat, when it starts to float. And then all the ice that flows through this grounding line actually elevates sea level. Once it is an ice shelf and is floating and has already displaced all the ice, the water that it will later take when it's melting. So, according to the Archimedes principle, there's no more sea level rise associated with the destruction or melting of ice shelves. However, the flow across the grounding line is what matters. And what was shown physically, without computers and anything, is now confirmed by computer simulations, is that the thicker the ice at the grounding line, the more flow you get through the grounding line. And you can see here what that means in a situation like West Antarctica, where the ice is actually grounded on the seafloor, so below sea level, and the seafloor is tilting downwards when you go further inland. In this situation, the grounding line, if the grounding line is moved backward inland, the ice at the grounding line is getting thicker. That means that there's more outflow through the grounding line, and you lose even more ice. It gets thinner, and the grounding line is moving even further inland. This is the kind of feedback that you can see here. It's a more complicated feedback than most other tipping points have, but it's one that's actually currently at play, because when you look at what happens with an ice sheet model, which is a very computationally very expensive computer simulation based on the basic physics of physical laws, that's the Newton laws basically, then you see if you destabilize in Amundsen Sea sector, which you see here, the Western Arctic ice sheet, the ice dynamics unfold precisely this as John Mercer has predicted 40 years earlier, 45 years earlier, or even longer. I'm getting older with time, obviously. Because the ice sheet is actually discharged into the ocean, the grounding line is retreating further and further, and you get a sea level rise of 3 meters only from this part in West Antarctica. West Antarctica is only part of the Antarctic ice sheet. The whole Antarctic ice sheet holds enough ice to elevate sea level globally by 55 meters. And there's another region in East Antarctica, which was also prone to a marine ice sheet instability and is also a tipping element of the climate system. It's not destabilized yet, but if you would destabilize it, then the same would happen as in West Antarctica. The ice sheet would discharge into the ocean, all its ice into the ocean, and would elevate sea level by another 3 to 4 meters. This is the biggest uncertainty with respect to sea level rise. There's another tipping point in the Greenland ice sheet, and I want to talk about this in a minute. But because it is so important in the political discussion at the moment, I would like to emphasize one specific tipping element that is not a tipping element, but has been discussed as a tipping element quite frequently. And that is methane, the permafrost thawing and the associated release of methane into the atmosphere. Methane is CH4, is also a greenhouse gas. It's actually 20 times more potent to trap energy on the planet than CO2. And we don't know how much methane is going to be released into the atmosphere by the thawing of the permafrost, both in Russia, in Siberia, and in Canada. Now, in principle, the global mean temperature and, for example, the thawing of permafrost constitutes a positive feedback which involves the global mean temperature. If you increase the temperature worldwide, you will increase the thawing of the permafrost. You will also increase the melting in the Arctic, and thereby reduce the reflection of sunlight near the North Pole back into space, and that also is a positive feedback. So it's increasing and it's been made positive by the fact that this thawing of the permafrost or the melting of the Arctic sea ice is increasing the temperature of the planet. The thawing of the permafrost is doing this through the release of atmospheric greenhouse gases, and this is increasing the temperature of the planet. So in principle, that's a positive feedback. And this has very often led to the notion that there is some unstoppable warming in our atmosphere that once we cross a certain threshold, we cannot stop anymore. Now I want to make this very clear. As I said earlier, the CO2 emissions that we have caused, caused in the past, are still warming our planet and are still increasing the temperature of our planet. That is an inertia that we have in the climate system. It is associated with these kind of positive feedbacks. But I said earlier, a tipping element is reached when these positive feedbacks start to dominate the dynamics of the system. Now, with respect to the global mean temperature and its feedbacks, we have an additional negative feedback that is overwriting all positive feedbacks. And that is the Blackbody radiation. It's a known quantity. There are no papers written about this anymore because it's at the heart of climate research, and we all know about this. But in the public, it's very often a lot of people don't know this. Now, this negative feedback is not killing the positive ones. It's not making them irrelevant, but it will always lead to the fact that the global mean temperature will stabilize. No matter how much CO2 we put in the atmosphere, and no matter how much this will increase the temperature of the planet also through positive feedbacks, the Blackbody radiation will always dampen the situation and stabilize the temperature at a higher level. But there will be no what's called a runaway greenhouse effect, which is self-amplifying. So there is no threshold in the global mean temperature beyond which there is an unstoppable warming, which is increasing with time, even if we don't emit any more carbon dioxide in the atmosphere. That does not take the threat of climate change, that does not reduce the threat of climate change in any way. We still have all the impacts. We have the sea level rise, we have the weather extremes, but it means that we as human beings stay in charge of the question of whether we increase the temperature of the planet further or not. If we stop emitting carbon, no matter at what level, we will stop the increase of the temperature of the planet. And that is very important because it puts the responsibility into our hands, as opposed to a threshold situation where we say, well, if we are beyond this threshold, we can't do anything anymore. It's out of our hands. It'll never get out of our hands. It's always in our hands. I don't want to give you the math of this. It's very simple. It's not invented by me, but I want to tell you that these feedbacks are important. They're baked into the climates in the climate models. There are some additional feedbacks. The ones that are in the climate models, they are they are the strong ones, and then there are smaller ones which are not taken care of in the climate models, and we are working on this, and the world community is working on this to incorporate them, but they will never lead to the to this threshold behavior of a runaway greenhouse effect. Now, I promised that I will talk about a few more of these tipping elements. I have to do this briefly because we want to get into a discussion, but let me briefly mention the Greenland ice sheet here, simply because it's related to what people call the Gulf Stream or the North Atlantic Current. And I wanted to briefly mention this too. The Greenland ice sheet is actually a tipping element that's quite easy to understand. The Greenland ice sheet has ice as thick as Antarctica, a little less thick. It's 3,000 meter in thickness, the ice sheet. And for those who have climbed mountains or just have a physics background, the higher you get in the atmosphere, the less molecules there are and the colder it gets. So this ice sheet is actually stabilized by the fact that it reaches into a very cold atmosphere. But you can imagine that if we melt a little bit of this ice sheet away, then it gets into warmer atmospheric altitudes, and there's more warming, and this and therefore more melting. And this actually leads to a threshold behavior. If you plot the temperature around Greenland on the x-axis here, and you observe the ice volume on Greenland, then you start here on the upper branch with a large ice volume. And then if you increase the temperature, you lose a little bit of ice following one of these lines here. This is parameter uncertainty. But there is a threshold of warming, if you have passed this threshold, then you cannot sustain an ice sheet anymore. You melt all the ice down to practically zero. Now, even if you reduce the temperature again, you don't go back the same path, but because it is so much warmer near the surface of Greenland, because it's not so high up in the atmosphere, you need much colder temperatures. You need to reduce the temperatures much more in order to reinitiate a growth of an ice sheet. And depending on which curve of these is a parameter uncertainty in an ice sheet model, depending on which curve of these are true, which we don't know at the moment, the statement is true that a Greenland ice sheet is there, that's for sure, but it wouldn't be there if it wasn't there already. If it hadn't, if it's there because there was an ice age before, but it wouldn't be there. It would not regrow if we melt it away. Now, very briefly now, this is the melt elevation feedback, but very briefly, let's get to the North Atlantic current and the Gulf Stream, or whatever you want to call this, the Atlantic conveyor belt, the Atlantic meridional overturning circulation, because it is a very important one. It's also a very uncertain one, and I don't want to leave here without at least mentioning it. The meltwater from Greenland into the North Atlantic actually lightens the water masses in the North Atlantic. And that could lead to a collapse of the so-called Atlantic meridional overturning circulation. You can see here the circulation path of the globe. And in the Atlantic, there's a northward current near the surface going past the Gulf region here. That's why this part is called the Gulf Stream, and then becomes the North Atlantic current. And then it gets to the north, and it's getting colder, and therefore the water masses are getting heavier, and they sink in deep water formation regions east of Greenland and south of Greenland in the Labrador Sea, and then flow back as cold deep water to the south. Now, because of this northward warm water flowing north, we are able to actually do agriculture in England, which you wouldn't be able to do without this current. If you go to the other, on the same latitude to America, you see this is a region where you cannot do the same agriculture as you can do in England. So what would happen if, due to a self-amplification feedback that is called the salt advection feedback, due to a perturbation of this system, for example, through Greenland melting, this Gulf Stream would collapse. We already see a reduction in the Gulf Stream strength, but a collapse would actually be a major hit to the climate system all around the globe. The North Atlantic, actually the Northern Hemisphere, would get much colder, actually by up to 8 degrees in some regions, but this would only be a redistribution of heat. Don't confuse this with the reduction of global warming. It'll only be a reduction in the North Atlantic because, first of all, the global warming pattern would add on to this temperature pattern here, and since it's only a redistribution of heat, the Southern Hemisphere gets even more warm due to this. However, if the Atlantic meridional overturning circulation collapses due to global warming, we'll have much bigger problems than this. Sea level will rise in the North Atlantic instantaneously by a meter. Precipitation in the tropics will change, will shift southward, will affect the Amazon rainforest, will affect the Sahel zone. The primary production will change due to this on land, and the ecosystem in the Atlantic will be strongly perturbed. There are also impacts onto the Indian monsoon and the Asian monsoon that have been observed in the past and have been modeled for the future in the case of this kind of collapse. So the Atlantic meridional overturning circulation is one of the big tipping elements of the climate system, next to the Western Arctic Ice Sheet, the Eastern Arctic Ice Sheet, the Amazon rainforest, the Greenland Ice Sheet, and monsoon systems on the planet. And I hope that you got a glimpse into the tipping elements and what they mean. The global mean temperature is not a tipping element. Thanks.
Yeah, thank you very much for this very clear and excellent presentation. Now, I would like to encourage all of you to raise your questions in the chat. Now, Anders, I would like to ask you one aspect. You emphasized that there is no tipping point in the global mean temperature. And to a certain extent, this is a little bit puzzling, because if you listen to the public debate from a certain distance, you get the impression that some, at least in the semi-scientific debate, people arguing that, for example, the 1.5 limit or the 2 degree limit is a kind of a cliff. So if we are at this limit, so and we cross this threshold, so then basically the Earth, the planet, will go over a cliff. And this is a very powerful metaphor, because it says we have to put all our effort into stabilizing or to respect this 1.5. When I get your argument here, so is this 1.5, does this mean there is room for more maneuvering to say 1.5, 1.6, 1.7 is also okay? So I would like to ask you to elaborate a little bit on this, because that's a very important message and a very important insight from your talk, but also from Working Group 1 IPCC.
Yes, well, it's I just want to make this concept clear again. If this would be the global mean, this would be this is the time when we cross the tipping point, and this is the temperature. If there was a critical temperature Tc, beyond which there was a threshold which would lead to unstoppable warming, then the situation would be such. This would be the forced situation caused by climate change, by the emission of carbon dioxide, right? We would, at a time Tc, we would reach this critical temperature Tc. And a runaway greenhouse effect would mean that if we stop emitting carbon dioxide at this point, we would still get a temperature increase like this. What actually happens if we stop at this point, we would get an additional warming, which we cannot stop anymore, but it would stop, it would stabilize. And this is the big difference. This is the runaway greenhouse effect, which a lot of people assume that there is a threshold temperature beyond which we will get this. And this is what actually will happen. There will be some fading out of our influence on the climate. There will be, the difference in the curvature is significant. So that doesn't make climate change, well, it makes climate change less dangerous in the sense that if we had runaway greenhouse effect, all hell would break loose, right? It would mean the extinction of the human race. But that is not something we have to fear. There is a lot that we actually have to fear, and it's mainly associated with the increase in weather events, in intensification of weather extremes. So there is actually the question whether 1.5 or 2 or 1.7 is the right temperature has to be determined by the impacts of climate change onto our society and onto nature. It will not be determined by the existence of a threshold temperature beyond which we're all going to suffer.
Yeah, thanks, Anders. Now, there are a few questions to Freddie from Peter Crampton. Peter, I cannot see you and I cannot hear you, but it's good to know that you are here. And the question of Peter is to Freddie, can you say something about extreme cold, such as occurred in Texas in February 2021, winter storm and so
on? Yes, in a minute. I'll just want to add to the question you posed to Anders. I think it's really, really important to remember that the 1.5 or 2 degree goals that we have set us are if you want, social tipping points that we have decided for as a global society in a sort of, to put it for economists, in a cost-benefit analysis, that because also 1 degree that we have now, 1.1 degree, is causing huge amounts of economic costs. People are dying, losing their livelihoods, and so on. And so that, and sort of, we have decided in weighing the impacts and what it will cost to reduce emissions to net zero ultimately, that it's just, that it's just not possible to do it above 1.5 degrees to deal with the impacts. But that's very different to a physical tipping point. But it's still a very important number, and it's not independent of the physical system, but it's not a number that comes out of the physical system without us humans. Now to talk about, I haven't looked at
Frederick, can I ask you a question here before you go on to the other question? So you have a training in philosophy. From my point of view, what you are saying is the following: talking about risk and damages is not unrelated to the underlying physics, but risks and damages and tipping point and acceptability. This is part of a decision theory, and this is about us as humans, and not just let's say something which can be derived from physics. Is that what you are saying?
Yes, you cannot derive it just from physics. It's ultimately an equity decision. So okay. Sort of who is paying, how much can we as a society afford to pay to let the most vulnerable, which are currently paying for the impacts, mostly pay for these impacts, and where do we have to put the line? Yeah. Okay.
Now to the extreme cold.
Yes. So extreme cold events are also happening in a warming climate, and I think this is really important that also in a warming climate where we have a huge increase in cold, in warm and in hot extremes and warm records breaking, we also can have record-breaking cold and cold extremes, but they are just happening less frequently, and the cold waves that are happening are less intense than they would have been in most cases without man-made climate change. Of course, there is this is the case for, this has always been the case for all cold events that we have looked at, but there are basically 2 ways of how climate change affects extreme weathers. One is the warming effect, so you have more greenhouse gases in the atmosphere overall gets warmer, so you have an increase in heat waves, decrease in cold waves, you have more water vapor in the atmosphere that needs to get out of rainfall, out as rainfall, so you have more heavy rainfall. But because we are changing the composition of the atmosphere and we have changing the temperature distribution in the atmosphere, that also affects the atmospheric dynamics, which means how weather systems move, how they develop, where they move. And this second effect is not the same everywhere, and it's very, very different from place to place, and it can go in the same direction, so that you have more weather systems conducive to rainfall, and you have the warming effect, so you get even more extreme rainfall, but they can also counteract each other, so that in some parts of the world you don't have a change in heavy rainfall because you have a bit fewer weather systems. And so it could be that in some cases there is that you have more weather systems conducive to cold, and therefore you have no change in cold waves or even an increase. We have not seen any observational evidence of this happening, but in models, and I'm sure that Anders will talk about it, in the theory, you could have an increase in cold waves in a warming world, but we don't have any observational evidence of that. So I'm sure, especially in a German context, you will have heard lots of discussions about the jet stream and jet stream weakening, which is something that can happen in a warming climate, and that could lead to more cold waves. But this is not what we currently have strong confidence in, that this is actually what is really what we see in the world, and we have no observational evidence. So for all the cold extremes that we have looked at, we have seen a decrease in the likelihood and intensity. But of course, they still happen.
Anders, before I hand over to you, you might add to that. I would like to raise another question, which refers to you. I read it out, and then you might comment on Freddie and also answer that question. So the question is, wouldn't the global mean temperature increase also being a tipping point if we know that global mean temperature is also a forcer for the ice sheet melting events, which are considered a tipping point? In a sense, global mean temperature increase would not be a tipping point for the temperature, but it could be considered a tipping point for the sea level rise. So, Anders, your comment, and then you might answer that question also.
So first of all, if we increase the temperature of the planet, then we can actually tip certain subsystems of the climate system, and this will also have an impact on the global mean temperature, but it will never be the case that this whole system, which includes the global mean temperature, becomes a tipping point. So a tipping point is that the system goes into a qualitatively different state, and this will not happen even if you, for example, melt away Greenland completely, and there's the Greenland ice sheet was white before and it was reflecting a lot of sunlight, and then there's the ground underneath and it's not reflecting sunlight anymore. That will have an increase in, that will result in an additional increase of the global mean temperature, but it will never spiral up into a hothouse. This is to the question. Regarding, I just wanted to support Frederick's statement and put it like a small twist to it. What Frederick was talking about, the dynamical changes in the climate system, on the atmospheric system, is, for example, a meandering of the jet stream here. And the statistics and the observations aren't there yet to say that this is happening more often under global warming. There are some theories that say because we increase the temperature, we reduce the temperature gradient from the North Pole to the tropics, because we are warming the North Pole much more than we warm the rest of the planet, that this jet stream becomes more unstable. And north of the jet stream, there's always cold air, and south of it, there's warm air. And we have seen, for example, in 2017, but also again in the winter afterwards, extreme snowfall events from Chicago to New York, which really halted the economic life there and the life altogether. And these kind of events could actually become more frequent under warming. But as Friederike pointed out, the observations aren't there yet. But it's very often very late if you wait for the statistics to occur. Sometimes also the physical argumentation is helpful. And I think we have some here, but it's not conclusive either. I'm in full line with Friederike there, obviously.
Okay, thanks, Anders. Probably you might stop sharing then. Yeah, we can see. Yeah, wonderful. Now there are two more questions to Freddie. So two from Nico Bauer. Recent extreme weather events in China seem very unusual or unlikely. Have you investigated these events and tested the attributability? That was the first part of the question. And second, it is common practice to run climate models with very different emission scenarios to see the incremental climate effect. What is the smallest increase in cumulative emission that leads to changes in model outputs that can be attributed to differences in emission scenarios?
So, so the first question, I haven't looked at the events in China, but colleagues in China have. But I have not memorized the numbers. But there are quite so. Chinese colleagues are actually one of the most active climate science communities doing attribution. So there are lots of attribution studies on different extreme events in China. But I don't know the numbers on the top of my head, but yeah, I'm very happy to send you the papers if you'd like. And well, what is the smallest increment or difference in emission scenarios or in emissions that you can still get a statistically significant attribution signal? That depends on the type of event. So we have done studies. So I have done attribution studies on how the emissions of different countries, rather than the whole global emissions, have changed the likelihood and intensity of different types of extreme events, and you get significant changes if you look at only the EU emissions, if you look at only the US emissions. So it really very much, but of course, the larger the signal, the more you can also statistically significantly see the discrepancies between small emission scenarios. And so it's a bit difficult question to answer, because it's often also the more models you use, the more you find that the models are actually the larger your uncertainty gets, because you have because you then have the systematic uncertainty in it, and not just the sampling uncertainty you would have if you use only one model. So it's a bit more of a framing question than a physical question, if that makes sense. But you can definitely show, depending on the assumptions you make, so which models you use, so within the same framework, you can show pretty small differences between emissions from individual countries or individual companies, or also just incremental changes in warming. I hope that answered the question.
Thanks, Freddie. So there is probably another question which refers to Anders. So the question is that, is it true that climate outcomes have been worse than the mean model predictions? And does this suggest that the models are missing key drivers?
No. Frederick,
okay.
Both in agreement. No, it's not. There are no key drivers missing, and the observations are, especially with respect to the global mean temperature, as Frederick showed very well, reproduced by the models, especially by the model mean.
I think there's a crucial misunderstanding here in this, because there is, so there are papers looking at damages from weather extremes and so on, and people have been surprised by the damages, but that is not because the climate system response is different than we expect. It's more that we discovered that our social systems and infrastructure are very vulnerable to even small changes in global mean temperature, and therefore extreme weather. And that is something where there are a lot of literature out there showing this. But this is a crucial difference between that the impacts in our social, human, natural systems are large compared to maybe what was estimated before in assessments of impacts, then this climate system response. That's really important to not confuse the two. We are actually really good in predicting the physical world.
Well, and perhaps, but we can go one step further and say that for a long time, we were very good at predicting the global mean temperature, and then we slowly got better and better in predicting also the smaller scale events. So the precise statistics of weather we cannot reproduce everywhere on the planet well, and in order to make studies like Frederick's, we have to get real good models. Let's put it this way. And they haven't always. They were first good at doing the global mean temperature, and now they're slowly becoming better and doing all the smaller scale stuff. So that is also something that's a step before. But we are, as Frederick said, we're pretty good at the physics now.
I would like to highlight one aspect here. This is a procedural one. This is the sixth assessment report of the IPCC, and it is the assessment report of Work Group 1, which is about the physics. In the next few months, we will see the publication of two additional reports, one from Working Group 2, which focuses very much on the impacts of climate change, and then Working Group 3, I don't know exactly when, I assume in March. So then there will be the publication of the Working Group 3, which deals with what is called the mitigation side and also partly on the adaptation side. I highlighting this because there's another interesting question, but it is very much a question to Working Group 2 and Working Group 3. Nevertheless, I will put this question on the table. So and the question is, looking at the historical records, to what extent the continuous increase of global mean temperature is associated with the change and continuities of economic and the political system, and what types of change do we need in the political and the economic system? So this is a typical Working Group 2 and Working Group 3 questions, but nevertheless, we have nobody here from that working group, and therefore I would like to ask Freddie and Anders at least to give a smart answer to this very fundamental question.
Well, we have someone from Working Group 3 here, don't we?
Yeah, but I'm no longer in the Working Group 3, and well, I would not be in a position to answer that question. So, Freddie, would you start and then Anders and then?
Sorry, which question?
The question is, if we look at the historical record, we see an increase of global mean temperature, but then the question is, what can we say about the increase of global mean temperature and what is the impact on the political and economic system? Here, I would like to highlight one aspect here, why this is such a delicate question, in particular for economists and social scientists, because at the beginning of the last century, there was a lot of debate in social science. So to what extent we are determined by geographical conditions and to what extent we are determined by the climate. And there is now, and basically all this geographical determinism has been rejected by the mainstream of the scientific community. A few people raised this issue again, like Jeff Sachs, and he basically came up with something where he wants to link social economic development with the increase of global mean temperature. So, but I just want to phrase it in this context, but nevertheless, I would like to ask you to share your insights.
Yes, sorry.
On this topic.
Sorry for sort of not putting the question together properly. So this is also a delicate question for me because I am on the synthesis report, so I know exactly what is in the Working Group 2 and Working Group 3 reports, but of course cannot talk about it right now. I think what is what has become very, very obvious also from the research on extreme events is that in many cases, the climate change signal is very small compared to changes in vulnerability and exposure and compared to just how much. So how much vulnerability and exposure determines damages from climate change and damages from the impacts of changing global mean temperature. And so that means that on the one hand, these changes are incredibly, they are so much more important in determining how we deal with climate change than the climate change itself. But it's also the case that social changes and having the governmental and institutional capacity to implement adaptation measures, mitigation measures are slow compared to the changes in the climate system. So the climate system, although if you just look at the magnitude of the change, They are relatively small. They are changing incredibly fast for a physical change compared to everything that our social systems have been developed for over centuries. And so that's why they threaten the developmental gains that we have, which means that we really need to try very hard to outpace climate change and to outpace our usual inertia in political changes to deal with this problem, if that makes any sense at all.
It makes a lot of sense, but this is definitely one of the hardest questions in social science. Anders, I would like to give you also the opportunity to respond to that, and then we are very close to the end of this great session.
I'm not sure I can say anything intelligent in this 1.5 minutes, but I can try. There's, for example, there was basically the same kind of hurricane on the same day, 16 years apart, hitting New Orleans. Hurricane Katrina in 2005 was one of the biggest impacts on the economy in the US from a weather extreme, and Hurricane Ida in 2021 almost had much less damage. So that shows that you can actually adapt and deal with this. But if you look into the correlations between extreme, temperature variability, annual average temperature, precipitation changes, and certain aspects like extreme rainfall events, and economic quantities like the regional growth rates, economic growth rates, not the national ones, but the regional ones, then you find correlations. They're not always a straight line. They're sometimes non-linear, but you find correlations between these in the observational record of the last 30 years. And that shows that at least as long as you're not aware of and you don't take serious the climate and weather extreme events, then you are highly vulnerable to climate change.
Okay, so we are very punctual. And definitely at the end of this great session, I would like to thank Freddy and Anders again for participating and share important insights on extreme weather events, tipping points, and on the report of IPCC Working Group 1. This was, I think, a very important contribution. In this seminar, we will also present Working Group 2 and Working Group 3. And it's the usual sequence. We start with climate physics. We want to understand what are the physical driving forces. But in the end, we came up with a decision theoretic framework, so to say, how to think carefully about risks, about damages, and in the end about our institutional capacity to cope with climate change. So with that, it's an open question, and we will try to answer these questions in one of the next seminars. But anyway, humankind has to answer these questions. I wish you a nice weekend, and I thank all the participants, and in particular, I thank all the panelists, and good luck, and I hope we will see each other very soon.
Thank you.